While early research into plastic pollution was limited to marine ecologies, the links between plastics and terrestrial and freshwater ecologies, food contact material, food production and human health are starting to gather apace. From the vantage point of a range of holistic, interdisciplinary and cross-cultural perspectives, plastics can no longer be treated as inert objects, but as unpredictable, lively matter. The complexities inherent in the way in which plastics are produced, consumed and discarded are never purely material, chemical, social or economic, nor are they stable. Regardless, and to our detriment, we continue to live with plastics as though they are inert physical materials. The reality is that the relational ontologies of plastics in food production and food contact materials challenge not only current food safety standards in Aotearoa, New Zealand, but also the notion that plastics can be captured within a circular economy. Plastics have revolutionised our lives. They've enabled the production of medical equipment and disaster relief items. They allow the minimisation of food contamination by harmful bacteria and reduce our foodborne illness burden. On the face of it, plastics are good. And yet, on the back of the wonderful advances that plastics have enabled, there are thousands of unnecessary uses that have developed simply because plastics are lightweight, cheap and disposable. Over 400 million tonnes of plastic are produced globally each year. Despite efforts to increase recycling rates, there is no sign of production slowing. Plastic production is expected to increase by 33 to 36% over the next 5 years. However they are managed, at the end of their useful lives, plastics find their way into ecosystems and anatomies all along the life cycle of plastics, from extraction to production, consumption to disposal, and legacy plastics. All of the 8.3 billion metric tonnes of plastics ever produced remain in the biosphere. They leave chemical traces all along their life cycle, and they degrade into microplastics from 0.05 millimetres to 5 millimetres in diameter, and then into nanoparticles, which are less than 0.05 millimetres in diameter. Just to give you an idea of how small that is, nanoplastics are small enough to pass through cell membranes. While much of the attention until now has been on marine plastic pollution, around 1/3 of all plastic waste ends up in soils or freshwater ecosystems. It's now looking as though terrestrial microplastic pollution is between 4 to 23 times higher than marine plastic pollution, depending on environmental conditions and pathways. For example, sewage sludge or biosolids is an important factor in the distribution of microplastics in terrestrial ecosystems. Most sewage systems are incapable of removing microplastics. 80 to 90% of the particles carried in sewage, such as from synthetic fibres, cannot be removed. Biosolids are often applied to fields as fertiliser, and it's estimated that globally this has led to several thousand tonnes of microplastics ending up in the world's arable soils each year. In New Zealand, biosolids can be composted with green waste and used as fertiliser, or landfilled or used for land rehabilitation. Some local councils in New Zealand have instead diverted their total biosolids production from landfill to vermiculture or worm farms. We'll come back to this little guy later on. Now, the term plasticulture is used to describe the modern practice of using plastics in agriculture. The plastic materials themselves are broadly referred to as ag plastics. Plasticulture, ag plastics, includes soil fumigation film, irrigation drip tape or tubing, nursery pots, and silage bags or wrap. But the term is most commonly used to describe all kinds of plastic plant or soil coverings, including plastic mulch film, row coverings, polytunnels, and plastic greenhouses. And what you're looking at here is a Kiwi version of plasticulture used for growing strawberries. The use of plasticulture is growing rapidly and perhaps nowhere more visibly than in Almeria, southern Spain, where the majority of its 30,000 hectares of land cultivated for food production occurs under plastic. The result is a plastic sea of greenhouses that can be seen from space. Polyethylene is the plastic film used by the majority of growers because of its affordability, flexibility, and ease of manufacturing. It comes in a variety of thicknesses, including low density or LDPE and linear low density or LLDPE. These films can be modified by including synthetic additives that have properties that are beneficial to plant growth, including to reduce water loss, UV stabilisation to cool soil and prevent insects, and anti-drip or anti-fog additives. Many of these additives are endocrine disrupting chemicals or synthetic hormones. These chemicals can disrupt gene expression, causing a wide range of hormone-specific diseases in humans and non-humans at extremely low doses. These are doses that are so low that they're measured in parts per billion or trillion. Common examples of these plastic additives are bisphenols, such as BPA, and phthalates, common in consumer plastics. If these ag plastics or films are not removed intact, they degrade into microplastics and their physical and chemical properties contaminate soil and water. Large amounts of residual mulch film can make farmland unusable, mainly through reduced water and nutrient movement. For this reason, some market gardeners are swapping out polyethylene ag plastics with BDMs, or biodegradable mulches. These are produced to be tilled into the soil after their useful life. However, a 2019 study found high baseline toxicity detected in all polylactic acid samples, or PLA plastics. Now, these are the most common bioplastics on the market today. BDMs have not been adequately tested for EDCs, or endocrine disrupting chemicals. The surfaces of tiny fragments of plastic have been described as plastospheres, or ecosystems that have evolved to live in human-made plastic environments. These plastospheres can house pathogens and persistent organic pollutants and transfer these into terrestrial and aquatic ecologies, humans and non-humans, and plants. The interactions seen when microplastics, soil, and earthworms come together were until recently undetected. That microplastics interact with soil fauna, affecting their health and soil functions, is where we get back to our earthworm. Earthworms make their burrows differently when microplastics are present in the soil, affecting the earthworm's fitness and the soil condition. Studies are beginning to show that the presence of microplastics in soils can stunt earthworm growth. In a UK-based study this year, different types of microplastics, biodegradable polylactic acid or PLA, polyethylene and microplastic clothing fibres were added to soil containing earthworms and planted with perennial ryegrass. When exposed to fibres or PLA microplastic, that's that bioplastic, fewer seeds germinated. There was also a reduction in shoot height with the PLA bioplastic. The biomass of ryegrass exposed to polyethylene was significantly reduced. Where polyethylene was present, there was a decrease in soil pH. The presence of microplastics also altered soil stability. These findings illustrate that microplastics can affect plant development and crucial soil properties, with potential further impacts on soil ecosystem functioning. An additional study shows that microplastics can accumulate in yeasts and filamentous fungi used to ferment and ripen foods. When plastics break down into nano-sized particles, there's a greater chance of uptake into plant roots. A set of 2018 and 2019 studies found that microplastics biopersist and translocate in plants and suggest that humans may be ingesting 80 grams per day of microplastics and nanoplastics via plant ingestion. Now, if this is true, it shows, as many predicted, that previous estimates that humans are ingesting the equivalent of a credit card of microplastics, or 2,000 fragments per week, is a gross underestimation. A credit card only weighs 5 grams. So the study offering the credit card analogy factored in fish consumption, drinking water, salt and beer, but excluded plants. Monomers and additives in plastic food packaging are increasingly linked to harmful health impacts ranging from birth defects to cancer. However, this is research that regulators are willfully ignoring. For example, a year-long investigation found that the US Food and Drug Administration and industry scientists continue to use decades-old study methods that fail to detect effects known to be associated with bisphenol A or BPA exposure. Hormonally active chemicals like BPA can exhibit unpredictable dose responses at levels way beyond those tested for health effects. In fact, 20,000 times lower. What this means is we need to overhaul the way we test agriplastics and food contact materials, such as HDPE milk bottles. HDPE has been found to leach non-intentionally added substances, or NIAS, and POSH, polyolefin saturated hydrocarbons, which have mutagenic and carcinogenic properties and have been identified as potential EDCs, endocrine disrupting chemicals. PVC flexible hoses for milk processing also needs to be adequately tested for EDCs, since heat and fat exposure facilitates the migration of phthalates from PVC into the milk. Many of our PET meat trays in New Zealand are now made from imported recycled PET pellets. These have not been adequately tested for phthalates, and the NIAS or non-intentionally added substances that are found in higher concentrations in recycled synthetic materials than in virgin plastic feedstocks. Plastics implicated in agri-food chains are useful studies for new materialist conceptions of distributed agency. These materials never remain within the temporal and spatial boundaries for which they were designed. They act in and with the world in often indeterminate ways, and with no end in sight as they become implicated with other things to create novel and often surprising ecologies. References to plastics' end of life is misleading. There is no end of life for polymer resins and their monomers and additives, and we're just only now beginning to understand the ways in which we are unintentionally releasing them into the environment at every stage of their life cycle. A circular economy will never retain our current plastics technologies. However, understanding plastic as leaky, active, and transformative will put us on the right path to a healthier future. I see an exciting future in the development of green chemistry and its potential to produce robust, reusable, non-toxic, and fully recyclable materials.